Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani. I am from Department of Computer Science, Arabic College, University of Delhi. So presently we are going through the series of operating system concepts, and on previous lectures along with the building the foundation about what actually an operating system is, we have also seen the internal macro view of an system, and we have also covered the concept of interrupt handling. Now within this lecture what we are going to cover is basically kind of divided into two parts. One is the storage structure and another one is input output structure. Now as far as operating system is concerned, why do we need storage, why do we need to study storage structure and input output structure? Because from the operating system's point of view, your operating system is going to interact with your input output devices, as well as your operating system is also going to interact with your storage devices and memory as well. So within the study of operating system, we need to understand the storage structure and input output structure from OS point of view. Now this is a very kind of well known fact that CPU can load only the instructions which are available in random access memory. So whatever data program your CPU is going to access, that should be inside your random access memory. And all the general purpose computers run most of their programs from this random access memory, which is rewritable memory, called the main memory, random access memory, or RAM. There are many kind of we can say name. And this main memory commonly is also implemented in semiconductor technology, which is known as DRAM, which is dynamic random access memory. So the technology in which it is going to be implemented is DRAM, and the running of most of the programs is done on the rewritable memory. Now apart from this memory which is RAM, we also have one component which is ROM, and EEPROM is also there. But you all are aware that this ROM is a read-only memory. You can only read that, it cannot be changed. So only the static programs are to be stored here. And what these static programs I am talking about is the most kind of we can say relevant example here is the bootstrap program. And also as the part of firmware, we have our EEPROM, which is electrically erasable programmable read-only memory that can be changed. Yes, it is not very convenient to change that, or we can say it cannot be changed very frequently, because this is electrically erasable and you need a special setup for erasing the contents of EEPROM. So this also contains mostly static programs. So now taking a kind of common examples of a smartphone device, we can say our EEPROM in the smartphone is there to store the factory installed program. Now let us try to understand the cycle in which an instruction is being executed inside the computer system. So a typical instruction execution cycle goes like this. The system first fetches an instruction from the memory corresponding to the command which is given, and store that instruction in the instruction register. There is a separate area for storing the instruction, which is known as instruction register. The corresponding instruction is taken from memory and being stored inside the instruction register. So instruction register is something in which the instructions which are to be executed next are put in up there, and the instruction is then decoded, and it may need some operands to be fetched from memory, and those operands may need to be stored in some other internal register. So this is kind of I can say the starting of a typical instruction execution cycle, that is taking the instructions from the memory, storing it in the instruction register, looking at this, decoding that instruction which is written inside the instruction register, and if it needs any operands, that operands are to be fetched from the memory. Then after the instructions on the operand has to be executed, the result may be stored back in the memory. So we are using this memory very frequently. So isn't it a good idea to store program and data, all program and data to be reside in the main memory? But can we do that? Ideally, these programs and data should be reside in main memory permanently, but two things, one is volatility and another one is capacity. So first is, we don't have random access memory in unlimited amount, we have a limited random access memory, although nowadays in modern computer system there is huge random access memory. The earlier systems were used to operate on some MBs of random access memory, but now we have it in kind of huge capacity, but still the capacity is a problem. Also it is volatile in the sense, whenever you are going to switch off the power, the contents will be deleted. So you cannot store anything permanently and in an unlimited manner on the random access memory. So what do? We have secondary storage as an extension of main memory. So now we have kind of our primary memory, and then we have our secondary storage, which is the extension, because to store everything inside the random access memory, that too permanently, is not possible. Now coming to what is the hierarchy of the storage. So if you can see here on the screen, there is a figure which says registers, then we have cache memory, then we have main memory, and other memories, and the last we have magnetic tapes. So this is a storage hierarchy. So from this figure, this is very, very clear that the storage which is available on top is very limited. The size of the bar is showing that is very limited, but despite of being that storage limited, this is very, very fast, because CPU is going to kind of access the registers at the first point, because these are the most these are within the processor. So then we have cache memory. This is as far as kind of amount is concerned, in what amount it is available, it is somewhat more than registers, also very fast. Then we have main memory, and then we have disk, and so on and so forth. So this is basically known as the storage hierarchy, and this storage hierarchy is arranged according to speed and cost. So higher levels are expensive, but they are really fast, and so is your registers and cache memory, but we cannot store everything on the higher levels because they are very, very expensive. So here is a trade-off between speed and cost. The more the speed, more the cost, and similarly vice versa. And moving down the hierarchy, the cost per bit generally decreases, whereas the access time generally increases. So there is a trade-off between the time and the cost. So the cost and speed increases, the time also I can say access time generally, the cost per bit decreases, access time increases, and vice versa. So there is a trade-off between the cost and access time. Now if we can see this storage structure, we have seen. Now our operating system is going to take everything from this either from this main memory, or we can say we have cache memory or registers memory, and we have one secondary storage, or like hard disk or magnetic tapes in, or optical disk or something of that sort, in order to supplement that main memory, because that main memory is kind of, we can say, is limited and also is volatile, and here is a trade-off between cost and access time. Now so this was about, I can say, storage structure, and this is the level of detail which we will be requiring in further exploration of operating system concepts related to storage. Coming to the input output structure, we have seen in the previous lecture that with each device we have a device controller, and there are multiple device controllers, and also the CPU are connected through a common bus, and this common bus is actually kind of, I can say, connected to the memory. So there are there is CPU, there are devices, corresponding to devices we have device controllers, and these controllers are connected through a common bus, and each device controller is in the charge of a specific type of a device. So device, and the in charge is the corresponding device controllers. Now within a single interface controller, can we have one or more devices, or there is to be kind of 1:1 relation, so one device, one controller? No, this is not the case. There can be one or more devices that can be attached to one controller. So here is an example, which is SCSI. SCSI is a small computer system interface controller, in which there are 7 or more devices attached to this particular controller in SCSI computer. So SCSI is a computer which is having I can say it's a small computer with a small system interface, and 7 or more devices can be attached to one controller. Now because there are multiple devices which are connected to this controller, this device controller also has some local buffer storage of its own and a set of special purpose registers. So device controller is also maintaining some storage in the form of local buffer and also some set of special purpose registers. Now what is the we can say job of this device controller? So we have seen that corresponding to each and device there must be at least one device controller. Now this device controller is responsible for moving the data between peripheral devices that it controls and its local buffer storage. So there is a peripheral device connected to the device controller, and there is a local buffer storage of the device controller. So device controller is in charge of data movement between these two locations, and typically operating system have a device driver for each device controller. Now with a device there is a device controller, and for a device controller there is a device driver. So that device driver is basically a program, or we can say a software which is related to a particular device. And what is the speciality of this device driver? This device driver understands the device controller and provides the rest of the operating system with a uniform interface to the device. Now let us try to understand this whole kind of flow in this way. With each and every device there is a device controller. That device controller is having some local buffer storage and some peripheral devices, and this local buffer storage and some special purpose registers are being maintained by the device controller, and device controller is responsible for moving the data between the device and the local buffer storage. And typically operating system have a device driver for each device controller. So there is a device, then a device controller, and then there is a device driver, and this device driver is going to communicate further to the operating system, because this device driver understands the device controller and provides the rest of the operating system with a uniform interface to that device. So now operating system is going to, we can say, communicate with the device ultimately with the help of a device controller, and that device controller is being understood by the device driver. So how a particular input output operation is being started? So in order to start an input output operation, the device driver, which is the software connecting the peripheral and the operating system. This device driver loads the appropriate register within the device controller. That means whatever registers are being are available inside the device controller, the value of those registers will be loaded by the device driver. When your device controller come to know that the instruction appropriate registers have been loaded, the job of the device controller is to examine the contents of the registers to determine what is actually required to be done, or what action is to be taken, what is actually written within that instruction. So device driver has loaded the registers, instructions are now with the device controller. Device controller will look into contents of these registers in order to determine what is to be done, what action is to be taken. Now what kind of these actions could be? This action could be as simple as reading a character from the keyboard, or maybe printing a line onto the printer. So this is kind of involvement of input output devices. Then what does this controller do? After checking the contents or after examining the contents of registers, when your controller is able to understand that what action has to be taken, the controller starts the transfer of data from the device to its local buffer. So I have already told you that the controller is something who is in charge of transferring the data between the device and the local buffer. So once the transfer of data is complete, the device controller informs the device driver via an interrupt that it has finished its operation. Now here comes the concept of interrupt, so which says that this whole process of I can say movement of data from input output device to the local buffer inside the controller requires the interrupt, or requires triggering of an interrupt. So the device driver, which is actually communicating with the operating system in real, then returns control to the operating system. Also we can say possibly it is returning the data or a pointer to the data if the operation was a read, and for other operations the device driver returns the status information. So whatever it is, the control, along with the control, the status information as well as the data which is to be returned to the operating system will be returned by device driver. But this whole process is taking place with the help of interrupts. So interrupt is generated, interrupt is being taken care of with the help of corresponding interrupt service routine. That interrupt service routine is invoked, and the data is being stored into the local buffer, or the registers have been loaded. For all form of this input output devices, we can say this is an input output cycle, which is an interrupt driven one. It is okay for moving small amounts of data, but it is producing high overhead, or it will produce high overhead when it is used for bulk data movement, such as disk input output. So disk input output is something which requires so for example you are opening a Word file, and that Word file is already having some 100 pages. So from that Word file from disk is to be taken to the random access memory or something of that sort. So now the device involved here is the disk, and the corresponding controller and the corresponding drivers will be involved. But with this bulk of data movement, this is kind of actually not reasonable to have an interrupt driven input output, because every time your interrupt is being generated, the normal functioning of your processor comes to a halt for some kind of a very small time, and then again it resumes. So it is okay for kind of a small amounts of data, but for large amount of data, such as data which is to be shifted to and fro between the disks, this is kind of very problematic. So in order to solve this problem, we have another method. Apart from this interrupt driven input output, we have direct memory access, which is known as DMA. Now what happens in DMA? Let's see. After setting up the buffers, pointers and the counters for the input output devices, the device control transfers an entire block of data directly to or from its own buffer to memory without any intervention by the CPU. The earlier interrupt driven input output was kind of we can say invoking an interrupt, and it is kind of we can say interrupting the process of or the execution which is being done by the CPU. But here, whenever the data block is transferred from the device controller to its own buffer, or maybe a device controller buffer and the input output device, or vice versa, the entire block of data is directly transferred to the memory and CPU is not at all involved. So this process is basically known as direct memory access, and in this process only one interrupt is generated per block in order to shift that block, just to tell the device driver that the operation has been completed, rather than one interrupt per byte which was generated earlier for low speed devices. Now please compare the two strategies. One is one interrupt generated per block without kind of disturbing CPU much. Another process says one interrupt generated per byte for low speed devices, and while the device controller is performing these operations, the CPU is available to accomplish other work because CPU is not being disturbed over here. So the two kind of mechanism, one is the interrupt driven input output, another mechanism is your direct memory access. So which one is more effective? Obviously for the bulk data we need to go for DMA, which is the direct memory access, and for this common we have a common bus architecture, or we have a common bus in between all the device controllers. So in place of this common bus, some high-end systems may use switches. And what is the I can say benefit of using switches? Multiple components can talk to other components concurrently rather than competing for cycles on a shared bus. On a shared bus, each device controller need to compete or need to kind of take up the memory cycles, and while a memory cycle is being taken up by one particular component, the others will others will be holding their operation of memory. But if we have a switch which is allowing these components to operate concurrently, so multiple components can talk to other components concurrently, they are not in a process of competing the cycles on the shared bus, rather they are having a switch. So if we have switch rather than your what we can say shared bus, having DMA direct memory access in these type of situation will become more and more effective as compared to the interrupt driven input output. So, what we have covered in this particular lecture is we have seen the storage structure from point of view of operating system, then we came to input output structure, and within that input output structure we have seen that how a device is actually going to communicate between the communicate to operating system or vice versa with the help of device driver and with the help of device controller. And while accessing this input output, what all could be the ways. So, there can be two ways. One is interrupt driven input output, another one is direct memory access. So, direct memory access is a better way for processing of or transferring of I can say bulk of data, and we have seen both the two methods in quite detail. So, this was for today. I hope you have enjoyed the lecture. Thank you. And here is a list of references which we have used in which we have used in preparation of this lecture. Thank you for a patient here.